So in this video, we're going to discuss about implementation of basic neural networks using NumPy. So we start by importing NumPy for all matrix operation and Matplotlib for standard 2D and 3D visualization. We also bring in Access 3D from MPL tools to enable 3D scatter plots. So Pandas is used to organize data into data frames for Plotly, which we'll use to create interactive 4D visualization. And then now we define the generate data function. So this creates a dataset with three input variables, x1, x2, and x3. So we generate each of them using np-random uniform ranging between -5 and 5. So we compute the output by using a custom nonlinear equation involving trigonometric and quadratic terms. This ensures the regression task is complex enough for deep networks to learn meaningful patterns. So after completing the target values, we normalize y to 0, 1 range for better numerical stability during training. And then we stack the three inputs into a feature matrix X, where each row is a training sample with three features. Once the data is generated, we reshape the target vectors to be a column matrix using a y dot reshape of -1, 1. And then now we're gonna x is of a shape of 1000, 3 and y is a shape of 1000, 1, which are ready for training. With our data ready, the next step is to visualize it 3D with color mapping, essentially a 4D view. So we'll use both Matplotlib and Plotly to help intuitively understand data before training. So after that, we define ReLU activation and derivative. This is the forward pass for simple epoch. So we're gonna do it for 1000 epochs. So the loss keeps on decreasing as the number of epochs increases. So this is the prediction on the new data. And moving on to developing a training a neural network using TensorFlow and Ensem. So we import the required libraries, NumPy, TensorFlow, and Matplotlib for plotting. We define a function to generate synthetic regression data using three input variables, x1, x2, and x3. And this is the visualization of the plot. We initialize the weight matrices W1, W2, W3 using HA initialization, which are suitable for ReLU activation. So we also initialize biases B1, B2, B3 to zeros. And then we define the ReLU activation and its derivative. Although activation is used in this TensorFlow model, back propagation is handled automatically by TF.gradient tape. Instead of using matrix multiplication with or tf.matmul, we're going to use an Ensem for matrix multiplication to compute dot products. And then we train the model over 2000 epochs using tf.gradient tape to track and apply gradients. And then we compute the MSE loss and take the gradients of all parameters and then update the weights using standard gradient descents. So you can see the loss decreases sharply after maybe 200, which is less than 0.3. These are the loss plots. Finally, we're going to test the model on a few randomly generated samples. So the predicted values looks reasonable and match the expected range of a normalized target variable. Next, we're going to discuss about PyTorch from scratch, therefore manual layers and no NN module. So we import the PyTorch and NumPy for computation and Matplotlib for 3D plotting. To ensure reproducibility, we set the manual seed for both NumPy and PyTorch. Next, we define a function to generate synthetic data using three input variables, and the target output y is a nonlinear combination of sine and cosine and polynomial and interaction terms. We also add noise to simulate real-world data. We used Matplotlib to plot the 3D scatter plot to visualize the training data in 4D. So therefore, three input features and one output encoded as color. And then we define ReLU activation function manually. Although we are using AutoGrad, this lets us stay close to how neural networks actually works under the layers. We manually initialize the weight matrices and bias vectors for all three layers using H initialization. Each tensor is wrapped with a dot requires grad to enable automatic differentiation. And then we train the model for 1000 epochs using a classic forward and backward pass. Then the loss is mean squared error, and we manually apply gradient descent using dot grade and dot assign sub logic inside a torch dot no grad block. You'll notice some instability during earlier due to random init, but training eventually stabilizes with a steady decreasing loss. Here we visualize the training loss in logarithmic scale, which helps highlight rapid improvements during the early epochs. After training, we make predictions on training data and store the outputs in YPredTrain. So all inference here is done by the torch.nograd for efficiency. So basically this plot compares the actual versus predicted, which is a perfect fit, would lie on the diagonal red dashed line. Our predictions are well aligned, confirming model effectiveness. So finally, visualize the model's predicted output in 4D space. This allows us to compare the shape of prediction surface with original data distribution. Next, we're going to discuss about PyTorch with NN module, therefore class-based neural network. We're going to import the required libraries. Then we define a function to generate synthetic training data with three input variables. And this is the visualization of the 3D space, and the output is encoded as a color, therefore the fourth dimension. Here, the main part is we define a class called neural net that extends NN module, NN dot module. So inside the constructor, we create three fully connected layers, which are 64, 32, and 1 neuron respectively. In the forward method, we apply the ReLU activation after each layer except the output. And then we initiate the model with model and set up the loss function as mean squared error. For optimization, we use Adam Optimizer with a learning rate of 0.01. And then the training loop runs for around 1000 epochs. In each iteration, the model performs a forward pass and then computes the loss, and it's going to run back propagation and updates the weights using optimizer.step. So as you can see, the loss decreases gradually from 244 to 0.4, so indicating that the model is learning well. So then we visualize the training loss using a log scale plot. This helps us clearly observe both early fast learning and gradual fine tuning. And then we evaluate the model on training data and compare actual versus predicted values. The closer the points lie to the diagonal red line, the better the model performance, and our points align very well. So we're going to reuse the 4D plot to visualize the model prediction across the 3D input space. Finally, we define a function to make predictions which are on new data, so which are manually specified input points. So the model outputs values that closely match the ground truth, showing the good generalization. Next, moving on to using Python Lightning version. First, we have to import the required libraries, NumPy, Torch, and Matplotlib for plotting. So then we define a Lightning module named Lightning Regression, which wraps the full model logic, which has a three-layer architecture using NN.sequential, a forward pass, a training step, a validation step, and the optimizer configuration. So training is launched using PyTorch Lightning Trainer, and then we set it to run for 200 epochs and enable logging. We're gonna so the trainer takes care of validation loops and device management automatically. Once trained, we switch the models to evaluation mode and make predictions. So this is the visualization of the 4D prediction and the color predicted Y. So using scatter plot, we visualize the predicted output against the three input feature. So we calculate the residuals, therefore the difference between true and predicted values, and plot them. A tight histogram around 0 confirms that the model is accurate and unbiased. We're gonna do on custom text predictions. We define a helper function to test the models on custom input points. The predicted values align closely with the ground truth for nonlinear equation, showing that the network generalizes well. Next, we're going to discuss about TensorFlow sequential API. So we use sequential API from TensorFlow to build a three-layer neural network for nonlinear regression using synthetic three-variable data. We begin by importing all necessary libraries, TensorFlow for model definition, NumPy for data handling, and Matplotlib and Seaborn for visualization. And then the generate data function creates synthetic regression data using three input features, x1, x2, and x3. And this is the 4D visualization plot of our training data. After that, we define a sequential model which has a dense layer with 64 neurons and ReLU, another dense layer with 32 neurons and ReLU, and a final output dense layer for regression. Then we compile the model using Adam Optimizer and MSE laws. Then we train over 100 epochs using 80% of data for training and 20% for validation. We plot the both training and validation loss on a logarithmic scale. The steadily decreasing curve indicates that the model is learning and generalizing well. And then next we use the trained model to predict on the entire training data set. We compare the actual and predicted values using scatter plot. The closer the points lie on the diagonal red line, the better the predictions. And then we visualize the predicted output across the 3D input space using a color-coded 4D plot. This gives a intuitive sense of the function the network has learned. And then we're gonna do a residual plot. So the difference between the true and predicted values are plotted here. The histogram shows the centered around 0, indicating unbiased errors. Finally, we test the models on custom input samples. As shown below, the predictions closely match with the actual outputs from the nonlinear equation. Next, moving on to TensorFlow functional API. First, we are going to import the required libraries, and then the generate function generates a synthetic data, and this is the plot of our data. So here we define a custom class by extending a tf.keras.model. In the constructor init, we build three dense layers with 62 neurons, 32 neurons, and one output neuron for regression. And the forward pass is defined in the call method using standard relay activations. So we compile the model using Adam Optimizer and MSE laws. So the training is split manually into training and validation sets. Then we train the model over 100 epochs with a batches of 32. So this is the training and validation loss. After training, we run predictions on full dataset using the trained subclass model. So this produces an array of predicted outputs for hybrid. Then we use a scatter plot to visualize how close our predictions are to actual values. So ideally, points should lie near the diagonal red dashed lines, which they do in this case. And then we're gonna plot a residual, so which are difference between actual and predicted values. So the then we sort the actual values and plot both the ground truth and predicted values. So the line graph allows us to see how closely the predicted curve tracks the true values. And then we evaluate the model and handpick test samples. For each 3D input point, we display both the model's prediction and the actual output from the target equation. So for instance, the input 4,4,4 and the predicted 25.58 and the actual 24.73. So this confirms excellent generalization. Next, moving on to TensorFlow subclass API. So we import the required libraries, we generate the synthetic data, and we plot the ground truth. So we're gonna define a subclass model. We initialize all weight matrices using H initialization and biases as 0. Then weights are defined manually using TF variable, enabling full control over training dynamics. And then instead of using tf.maximal, we perform all matrix manipulation using nsum. So the model has three layers, each followed by ReLU except the output. We train the model for 1000 epochs using TensorFlow low-level grade AM tape. In each iteration, we're going to compute predictions, calculate MSE loss, derive gradients manually, and update weights using assign sub. As training progresses, we can see the loss increases from 5.2 to 1.4. Then the log scale log loss gives a clear view of how the model is improving across epochs. It starts high and gradually levels off as the convergence is reached. So then we compute the residuals. It's the difference between actual and predicted values. And we're going to plot them. A roughly semantic distribution centered around 0 confirms that the model is unbiased. Then we visualize the predictions using the same 4D scatter plot. By sorting the actual outputs and plotting both actual and predicted values, we have a nice visual representation of how well the model tracks the true output range. After that, we add the model on three custom test points. So the prediction and the actual scores are good, are in close match, indicating our model performed well. Next, moving on to low-level neural network. So we use the generated dataset, synthetic dataset. We initialize the parameters using H initializer. We're gonna run 4,000 epochs. As the epochs increases, the loss is gonna decrease, indicate the model is running well. Is the overall training loss. So the graph of actual versus prediction is more or less more of our points are closely centered, indicating the model is performing well, and we can also see the residuals are almost centered at zero. And this is the 4D visualization of our predicted values. So we can see the ground truth versus the predictions. So after that we test on custom predictions. This values indicates that our model is performing good. Next moving on to TensorFlow built-in layers. So we're going to use TensorFlow sequential API with built-in layers as diagnostics. We import the required libraries. Here also we're going to generate specific data set. After that we're going to visualize it. Here we define a sequential API with 3 dense layers, 61 neurons with ReLU, 32 neurons with ReLU, and 1 neuron for regression output. Then we compile the model using Adam optimizer and MSE loss. So we train it on 80% of the data of 400 epochs with 20% used for validation. So we run predictions on entire dataset using trained model. And then this scatter plot shows how close the model predictions are to the true values. The red diagonal line represents perfect predictions and our model performs very well. Then we plot the residuals, which is the difference between actual and predicted values. A symmetrically centered histogram indicates unbiased prediction errors. And then this 4D scatter plot shows the predicted outputs in the same space as our inputs. So this confirms whether the model's predictions resemble that of the actual data structure. Then we sort the true y values and plot them against the predicted values. Therefore, the two lines closely follow each other. Another strong signal of good learning. Then we test the model on 3 custom inputs and compare predictions against actual computed values which are directly from the nonlinear function. Therefore, input 4,4,4 and prediction 21.59 and actual 24.73, which is a strong match with a low error. So this set of scatter plot shows how the prediction error varies with each input feature. Therefore, the red horizontal line indicates zero error. This helps identify any feature introduces bias or overfitting. And then we use gradient tape to compute partial derivatives of the output with respect to of each input feature. Then we take the average of the absolute gradient to estimate each feature's influence on the model's output. Here we can see that the input model is more sensitive, which is helping us to infer the model's behavior. Next, moving on to neural network using JAX. So we've built a fully manual relay neural network using JAX, leveraging the advanced features like JIT, GRAD, VMAG, and TreeUtil. We implement for propagation, training, diagnostics, and feature sensitivity all from scratch. We begin by installing JAX and importing all necessary modules. This includes JAX.numpy, the random key generator, and AutoGrad tools and visualization libraries like Matplotlib and Seaborn. Then we set a reproducible random seed and define a custom nonlinear function using sin and cosine and xq. So this generates synthetic 3D inputs and corresponding outputs and with added noise. Then we visualize the data using a 3D scatter plot with color-coded output to understand the regression surface the network will learn. Then we initialize the network weights using HA initialization and store them in a Python dictionary. So the model has 3 layers, input with 128 and other one 128 to 64 and 64 to 1 output neuron. So the forward function performs a full forward pass through all layers using JNP dot function and ReLU activation. The output is a single scalar per sample. Using JIT, we compile the prediction and gradient functions for speed. And the treemap function allows us to update every parameter using the corresponding gradient. After that, we train for 1000 epochs, computing loss and updating weights manually. Every 100 epochs, we log the current loss to monitor progress. So we plot the training loss, compare actual versus predicted values, and visualize the residuals. The residual shows a good regression fit with low error. So here we sort true values and plot predictions to evaluate smoothness. We also test custom inputs and prediction match actual values closely. So we compute the RMSE as a final performance metric. In this run, the final RMSE is approximately 3.9, and we use a VMAP to compute the MSE for each sample individually, then plot the sorted per sample loss. This helps us analyze where the model struggles. Then we compute the gradient of the model output with respect to each input feature. So the average absolute gradient gives us feature sensitivity, which is plotted as a bar chart. Then we demonstrate how to flatten the model parameters for advanced inspection or saving. Then we use JIT compile to forward pass, confirming that JAX executes it efficiently. After that, we finally save the predictions, residuals, and input to a file. Thank you.